Hello, good afternoon. Hello. I think it's time to start. So welcome. Good afternoon once again. So today we will have two talks. The first speaker will be Lorenzo Di Pietro from the University of Trieste, and he will tell us about conformal boundary conditions for free fields.
Thanks a lot for the invitation. Yes, sorry for the typo in the first slide. Today it's 23, not 24. So the topic of my talk indeed is conformal boundary condition for free fields. And oops, I pressed something wrong, maybe. And so let me start by introducing the concept of a conformal boundary condition. So by that, we simply mean that we have some conformal field theory in flat space, say with a flat boundary. So there is some coordinate who is restricted to take only positive values. And we need to impose then some boundary condition on the hyperplane where this coordinate is, say, 0. And we will call conformal boundary conditions, or equivalently, we use the term boundary conformal field theory, a boundary condition which preserves the largest possible amount of conformal symmetry compatible with this geometry. So in this case, this would be the one lower dimensional conformal group, which you can imagine acting on this hyperplane. And physically, these conformal boundary conditions describe the phenomenon that in statistical physics sometimes it's called surface critical behavior. So what does that mean? So imagine you have some material which undergoes some second order phase transition. So it's described by some CFT. So this will be the bulk CFT. And then this material will be, let's say, limited, will be enclosed in some finite region, and it's interesting to see what happens near the edge of this region. And what happens typically is that we will have some different set of scaling exponents, correlation functions with decay with different exponents which are not the same that we find in the bulk. And a given conformal field theory in the bulk, a given transition in the bulk can have different set of exponents which are organized in different universality classes. And these different universality classes are what correspond to the different possible conformal boundary conditions for the bulk CFT. Here I just depicted the, let's say, the prototypical example, which is the one of the Ising model. So let's say we have our system of spins in a region which is finite, and then at low temperature, we are in some ordered phase, and then we have a transition disorder one, and at the critical temperature we have the second order transition. But then even if we just tune to the critical temperature, we can still change an additional parameter, which is the relative strength of the coupling between spins on the surface compared to the bulk. And if we vary this parameter, we can have different kinds of correlators in the surface, which are just correspond in one-to-one correspondence with the different possible conformal boundary conditions for the Ising CFT. Okay. So along these lines, we have different possible conformal boundary conditions. Okay. So as I already said, so the observables in this setup are the interesting observables are like given by considering local operators inserted on the boundary of our region. And we want to study their correlation functions. And as I already said, there will be different scaling dimensions compared to the bulk. So there are a new set of CFT data. And if we just consider these correlators, they look in all the possible ways, they look very similar to the ones of a lower dimensional CFT, except there is a very important difference that since we have this coupling to the bulk, in general, we will not have a stress tensor in this conformal, let's say, lower dimensional conformal field theory. because it's non-local, let's say. There is a loss of locality due to the coupling to the bulk. So the central question in this kind of problem, one very interesting classification problem that arises is if I give you a certain bulk conformal field theory, what are the possible conformal boundary conditions? And this is a very hard question, and I will not solve it at the end of this talk, but and indeed we don't know much about this question except the case of two-dimensional rational conformal field theories. So in this problem of exploring the set of possible boundary conditions, on one hand, if we use like RG intuition, this seems to be a very hard, almost hopeless problem, because suppose we start with our bulk CFT and we fix some initial boundary condition, then it seems that we can generate new ones by just adding some local sector now living on the boundary, some additional degrees of freedom, and for instance, coupling some operator of the UV boundary condition to some operator of the local sector. And then this, if we arrange things in such a way that this G is relevant, we would imagine that this will trigger some RG flow, and then we would end up in some new IR conformal boundary condition. And so it seems in a sense that the space of conformal boundary condition is almost as rich as the space of one lower dimensional CFTs, and that we can take for granted it's a hard problem. There is, however, a possible loophole in this logic, which might give us some hope, which the loophole is that in principle, it's a logical possibility that when we try to do this, many times we actually end up in an IR point in which, again, the bulk and the boundary decouple. And so if that happens, it could be that we just end within a small set of boundary conditions. Okay. So this is still in the motivations. And so given that I try to convince you that this problem seems hard, methodologically sound approach seems to be to start.
Sorry, Lorenzo,
yes?
I have a question. So is there some way in which one could claim that some boundary conditions do not add the degrees of freedom, only use the degrees of freedom in the bulk? I mean, is there some way in which one can define this concept, or it makes no sense?
Repeat what concept?
So a boundary condition that does not act, that does not add new local degrees of freedom at the boundary, in some sense, only uses the degrees of freedom of the bulk.
I don't think it's such a concept. No. I mean, of course, you can detect if there is a decoupled local sector, but because there is a stress tensor then on the boundary. But I think, in fact, you can, perhaps there could be some dualities that relate stuff that you would say contains boundary degrees of freedom with stuff that does not contain boundary degrees of freedom. So as I was saying, it seems like a good starting point would be to consider to first simplify as much as possible the bulk, and then to attack this problem in this setup. So that's what I'm going to talk about today. And what does it mean to simplify at most the bulk? It means to consider conformal field theories of free fields. And so the setup we will consider is the one in which we have indeed the free bulk to allow, in a loose sense, interactions with boundary degrees of freedom, and we want to look at possible fixed points. So as for the reason I just explained, this will describe boundary phase transitions or surface critical phenomena in systems which are the bulk by free fields. And so the plan of my talk is that in the first part, after some introduction to the more technical aspects, in the first part, I will try to convince you that even if we restrict to free fields, it's still a rich enough classification problem. And I will try to convince you of that by showing some examples. And then in the second part, I plan to tell you that is anyway simple enough to be worth trying to attack using the technique of the numerical conformal bootstrap. Okay, and please stop me, of course, at any time for questions. And I just want to mention briefly that even though we consider just free theories in the bulk, this is not completely academical. There could be applications even to this case. For instance, if we consider the CFT of a free scalar, we could still view this as the CFT that arises in IR of a Goldstone phase, let's say in 3 bulk dimensions or 4 bulk dimensions. And in 3 + 1 dimensions, so in 4, sorry, let's say 4 dimensions, the Z2 breaking transition is indeed described by a free scalar. So, and in the case of the Maxwell field, which we will also analyze, we will see that actually the space of boundary condition is very rich, and it will lead to a let's say, new way to think about and connect with each other 3-dimensional abelian gauge theories. Okay.
I'm sorry.
Yes?
You know that in 2-dimensional conformal field theory there is a huge work on this, right?
Yeah, I will most talk higher dimensions, but yeah, I briefly mentioned that. I mean, I know that the case of rational conformal field theories, of course, it's sort of classified. What are the possible conformal boundary conditions? I don't know much about the work in the non-rational case. Maybe there is some story there, but I'm not. A compact boson.
At least I guess the topological defects have been.
Sorry, can you repeat?
So the compact boson in
Yes,
2D, I mean, it has
2D.
many non-rational points. I mean, is there a full list? Of course, of the rational points, as you said, there's a list, but what about the non-rational points?
I think it would be, I would guess that it's almost as complicated as the cases I'm studying here, but I don't know. I didn't really look
So I know the topological defects at least are classified. I don't know about the conformal ones. I guess once you have the conformal ones classified, then you have the boundary conditions too.
I mean, I'm not aware of a classification in that case, but it would more or less fall in the category of conformal boundary condition for free fields that I'm studying here. And some of the things that I'm talking about could be applied, but there is a difference because here I'm going to talk about free scalar, for instance. But in that case of the compact boson, you cannot really use the bulk field of the scalar because it's not well defined, because it's compact. Well, many things that I will say will rely on using this operator. So, okay. In order to now make a little bit more precise this concept of interacting boundary condition, let's start with the free ones, and then we will go to the interacting. Okay. So let's say we have a free scalar. And again, we are in this setup with a boundary. And let's remind ourselves what we do without an interaction. So in this case, we have bulk equation of motion that tells us that when we push this operator close to the boundary, we can have 2 possible boundary modes. One is associated to just restricting the scalar to the boundary, and the other one is the normal derivative. And if we require stationarity of the action, we can rely on the Lagrangian here because the theory is free, so everything is simple. With having interaction, then basically we find that there are 2 options. Either we have to set the phi mode to 0, and this is what we call Dirichlet, or we have to set the normal derivative to 0, and this is what we call Neumann. And of course, if I don't care about conformality, I could do more general things. I could perhaps put some constants on the right-hand side of the equations, or I could consider linear combinations. But all of these things would break conformal invariance. So if I don't want to break conformal invariance, these are the only 2 options, interactions, without boundary interactions. And there is a very similar story if I consider other kind of free bulk theories. For instance, if I do a free Dirac, I would have still 2 modes. This might sound familiar from, I mean, also from ADA-CFT. It's a very similar story. You know, we always have 2 modes at the boundary. And this would be sort of the 2 chiralities of the fermion when we restrict it to the boundary, or for free higher 4-gauge fields. For instance, in 4 dimensions, this would be Maxwell theory. And in this case, we would have the two possible modes are two conserved currents, which you can think of as one electric and one magnetic one. And without any interaction, you have to pick which one you set to 0. Okay, so this is a generalization of Neumann and Dirichlet for other kind of free theories. Now, so summarizing in this case without interactions, we always have, let's say, two possible modes, and we need to kill one of them. One of them is set to 0. And there is a very important concept in boundary conformal field theory, which is the boundary of P, which means what happens when we take the bulk operator and we push it to the boundary, and we can write it as a sum over insertions of primaries of the boundary. And so in all these cases without boundary interactions, what will happen is that in the boundary of P of the field, of our free field, there is going to be only one primary of the boundary, okay, which is the mode that we didn't kill. And the boundary theory is then very simple. One can show that it's just the mean field theory for the surviving operator. Mean field theory, sometimes we call it generalized free field, or it just means that all the correlation functions are computed by weak contractions. Okay, so this is the case without interactions.
Sorry, Lorenzo, yes? Can you tell us why you cannot impose, set to 0 some linear combination of the two operators?
So in the case of the scalar, it's kind of clear because they have different scaling dimensions. Yes. In the case of the gauge field, it's not so clear, but I'm just saying what from bearing the action without having anything on the boundary. So if you do just this, the variation of the action, then you do find that there are, because basically there is something that couples the two modes, and therefore you need to set to 0 one of them. Okay, there is a way to realize in the case of the gauge field, for instance, there is no obstruction to consider linear combination of these two because they're both conserved currents, but actually that does require to add some degree of freedom on the boundary, which is going to be in the case of the for the Maxwell just some Chern-Simons theory basically, and then you can get also the linear combinations. Okay, now having built some understanding for the case without interaction, let's build some intuition for when we turn on the interactions. So let's consider again the free scalar, and now I couple it to some operator of a lower dimensional local sector, okay, so lower dimensional CFT that I put there. And what happens if I do that? Again, I go through the variation of the action, and now I discover, so I started with Neumann for definiteness, and now I discover that the normal derivative is not anymore set to 0, but it's actually identified with the operator of the conformal field theory that I added on the boundary. This is what you can call modified Neumann. And generically, this will start some RG flow on the boundary. But the interesting thing is that after we do this deformation, both the field and the normal derivative of the field are going to be non-zero. And I might expect generically to end up in a conformal boundary conditions where both of these modes are turned on. Okay, so I'll use this to now formalize the concept of an interacting boundary condition, interacting conformal boundary condition. So an interacting boundary condition for free fields is going to be any conformal boundary condition in which both the modes that we described a minute ago, they need to both be non-zero. Okay, so they will both exist in the spectrum of the boundary theory. Their scaling dimensions are still going to be fixed by the bulk equation of motion, but they will both be non-trivial. And in this case, the correlation functions are not given by weak contractions. They're going to be some complicated correlation functions, which is not mean field theory. Okay, so this is the formalization of the idea of interacting boundary condition for a free field. Now, I'm going to now discuss some examples, as I promised, and then we'll see how to attack this problem with the numerical bootstrap. There are questions about the definition of interacting boundary condition? Okay, so
yeah, so I'm sorry. Can I ask another question?
Yeah, sure.
So is it obvious that there is no RG flow in the bulk, which is triggered by the boundary coupling? Because so one could imagine that if you take an operator which is not marginal, so doesn't have the correct dimension, but then you put a coupling constant in front of it, which is 1 over R to a suitable power to make it scale invariant. So I mean, it will decay as you go away from the boundary.
You mean if you can generate space-dependent?
Yes.
I think that you can rule out by using the word identity of the bulk stress tensor. I mean, this is not possible. Now, if you ask me the mathematical proof, I need to remind myself how you do it, but it's by using basically the word identities in the bulk. In general, the logic is that, so what you need to keep in mind in this business is that whatever you do on the bulk or the boundary is not going to back react in the bulk. So by locality, let's say, if I turn on some coupling here, this is not gonna generate couplings in the bulk. This is kind of easy to understand for space independent couplings. It's a bit more tricky if you want to think about allowing space dependence, but it turns out also to be true. So the first example that I want to mention, I studied this in a paper 2 years ago with Davide Gaiotto, Edoardo Lauria, and Jingshang Wu, is the case. So we'll start from the spin 1 and then go to spin 0. Is the case of the 4-dimensional Maxwell conformal field theory. So just considering the bulk, the Maxwell Lagrangian, also allowing theta term. And as I said before, in this case, the two operators are the electric and magnetic conserved currents on the boundary. And how do we define some interacting boundary condition? Well, it's very simple. We just put some 3-dimensional CFT with a U1 symmetry on our boundary. And then we can starting with Neumann for the gauge field. We can turn on this coupling between the boundary value of the gauge field and the current. So in a sense, gauging this current with the bulk field. And this lead to this modified Neumann boundary condition. So the original Neumann was when JA was 0. And after we turn on this interaction, JA will be identified with the current of the CFT. So I will be brief because I want to discuss also other examples, but let me just tell you what is the upshot of the analysis that we did in this paper. So the upshot is that actually in this case, one finds a conformal manifold, let's say, of boundary CFTs, of conformal boundary conditions. And the basic reason is exactly what we discussed with Francesco before, that coupling tau, it's the gauge coupling. In this case, is actually best thought about as a coefficient of a bulk operator. So coefficient of a bulk operator cannot receive renormalization by any kind of interactions which are localized on the boundary. And so whatever CFT we are gauging on the boundary, tau will remain just a free parameter. And we have this family of boundary conditions which are labeled by points on the upper half plane. But what is more interesting is to try to understand the various decoupling limits between the bulk and the boundary. So obviously by construction, there is one in which we send the coupling tau to infinity in the upper half plane, meaning that we turn off the gauge coupling. And if we do that, we are just going to find the Neumann mean field theory, which is the mean field theory of the, let's say, magnetic current. And we're going to get the 3-dimensional CFT that we gauged a second ago, because the two are going to decouple, right? If I send the gauge coupling to 0. But then suppose instead we go to one of the cusps on the real axis, which are all the rational points. Then what we discuss in our paper, and it's kind of maybe intuitive due to electromagnetic duality in the bulk, is that one is going to find at all these rational points a new decoupling limit. In this new decoupling limit, one again finds a certain linear combination of the currents, which will be, let's say, the non-local sector coming from the bulk, and a new local sector appearing, which is not the original CFT we started with, but it's like the gauging of this conformal field theory in 3 dimensions. So it's like the original theory coupled this time to 3-dimensional gauge fields and flowing to the IR of that. Okay, so this operation of taking a CFT in 3 dimensions with a U1 symmetry, engaging the U1 is part of, for those of you who know of this SL2Z duality group, SL2Z group acting on CFTs discussed by Witten. And what this construction of the boundary condition gives us is a continuous interpolation between all the different CFTs in a certain orbit of the SL2Z. Okay, so this was like a very brief description, but the upshot is that the thing I want to, the message I want to pass is that in the case of the gauge field, we do find a very rich set of boundary condition, and it seems somehow to be very close to our RG intuition, meaning that basically almost every theory that you can couple is going to give rise to a conformal boundary condition. Now let's consider different, so if there are no questions about this, yes?
Didn't you say, maybe I misunderstood, didn't you say at the beginning that only the one with 0, that Neumann with 0 was conformal? That Neumann with 0 on the right-hand side, but now we find that J is equal to J CFT is also conformal, or am I misunderstanding something?
No, what I said before was that if you don't have any interactions on the boundary,
then
okay,
you can't see.
then it can only be either J equals 0 or I equals 0, what I call J and I.
Oh.
Then in the more general case,
Okay,
is what can happen.
Sorry.
Okay, and so the second example, so here we saw a very rich case. The second example, this is based on a paper that I wrote last year in collaboration with Edoardo Lauria again, and Pierluigi Niro, who is here in the audience. So let's try to build again some examples in the case now of the 4-dimensional free scalar. So if we want to try to get some example under perturbative control, we need to somehow couple to some degrees of freedom, which are a 3-dimensional CFT, which is under perturbative control. Otherwise, we will run into strong coupling. And the idea that we tried is to use large n on the boundary. So the simplest possible CFT under control, at least to my knowledge, is to take, for instance, the large n vector models. Let's say the case in which we have n free scalar fields. And we also have the version which is critical ON model, in which these n free fields, we also allow them to have some quartic self-interaction. And this is an interacting CFT, but it's solvable in the 1/n expansion, okay? So these are 2 examples of CFTs under control. And let me remind you that these 2 CFTs, the free and the critical ON model, they have a singlet scalar operator of dimension 1 in the case of the free scalar. This is just this phi I, or dimension 2 in the case of the critical scalar. So this is like the operator that replaces phi I in the critical theory, and that's dimension 2. So we find that this number 1 of 2 are very lucky because we can build these 2 marginal interactions between, let's say, the normal derivative of the bulk field and the free bilinear, or we can start with the Neumann boundary condition and couple it to the critical ON model. And we have these 2 marginal interactions, G and G prime. And so our hope was, let's consider these couplings, turn them on, and perhaps we will have the flow under control, and we will flow to some interesting boundary conformal field theory. But what we discovered was a bit different. So what you actually find is that actually turning on these two interactions leads to one and the same RG flow, just from two different points. So this RG flow can be solved exactly at Largen, and you find that in this interaction between the Neumann and the critical scalar is marginally relevant. The interaction between Dirichlet and the free scalar is marginally irrelevant. And there is, so the two fixed points are both decoupled, okay, between the bulk and the boundary. And the interesting aspect that we discovered is that you find this interesting RG with a duality. We have let's say, a strong weak duality between the two descriptions from the UV and from the IR. Another interesting aspect of this construction is that we find, let's say, a new way to connect the free and the critical ON models, which doesn't involve at all any, let's say, massive coupling. We just have these marginal couplings, a log running RG that goes between the two. But so there are a lot of interesting aspects of this story, but from the point of view of finding interacting boundary conditions, this seems to go in the other direction. What we said, that sometimes it might happen that you try to start an RG, but then you end up in a decoupled situation. So other questions about the example? So somehow the simplest attempts in 4D don't seem to give new boundary conditions between Neumann and Dirichlet. Okay, the final example I want to discuss. This is going to appear in a paper that I'm now writing in collaboration with Conor Behan, Eduardo Lauria again, and Balt van Ries. And let's consider now an example with three-dimensional scalars. So here it turns out that you can do the following. So you have your free scalar in the bulk, and you consider now minimal models on the two-dimensional boundary. And let's start with the Dirichlet boundary condition for the bulk scalar, and then we can consider this interesting kind of deformation in which we have, so this the minimal models are labeled by this M, and then where M equals 3 is the easing, and then it goes all the way to infinity. And these O13 and O12 are just the way we usually label primaries in the minimal model. This O13 is in the easing would be the energy, and the O12 is the magnetic, the spin field. And it turns out that you can solve this in the large M limit, okay? So in the large M limit, in which the central charge is approaching 1, the dimension of this O12 operator approaches 1/2 with 1/r corrections, and the dimensions of the energy, let's say, operator approaches 2. So both of these couplings are close to marginality, because remember now phi has dimension 1/2, it's a bulk, it's a three-dimensional scalar, so the derivative has dimension 3/2. So both of these are nearly marginal on the boundary, and you can just work out the exact form of the beta function, and you find that there is indeed a perturbative fixed point where both of these couplings are of order 1/m. So again, this seems to behave.
So you need both G and G prime different from 0 to get the fixed
both
point.
G and G prime different from 0. So for instance, if I would have got a fixed point with just G different from 0 and G prime 0, be boring because it will not be coupled to the bulk. Actually, that of course exists because it's the famous RG between two minimal models, which is just triggered by O13. But there is also this other fixed point in which you have also G prime turned on. Okay. So, yeah. No, indeed. In the IR fixed point, actually what happens is that, you see, since O12 is the one that I'm coupling to the normal derivative, this is going to be the one that in a way recombines with the phi hat, like the restriction of the scalar to the boundary. So the dimension, the IR dimension after this RG of this is going to be fixed to exactly 1/2.
Ah, okay.
Yes.
Because this is, so the scaling dimension in the bulk is not gonna change. This is just fixed to be
The bulk
1/2.
is the free scalar, okay? So it starts with 1/2 plus a correction of order 1, and in the IR is going to be exactly 1/2 because it's fixed by the fact that it gets identified with the restriction of the scalar to the boundary.
So this is a generic feature, I guess. When you couple the boundary CFT to the bulk, then you know what is gonna be the scale.
Yeah, at least there is going to be two protected operators, which are the restriction of the field to the boundary and the restriction of the derivative of the field. So these two guys are not mysterious, their dimensions are known. But then there is going to be all the rest of the guys, and those I don't know anything about. I mean, I need to, okay. I didn't put just because I wanted, but it gets generated. Yes, I cannot avoid adding it. Yes. If I just have this other guy, this will generate G.
Okay. Sorry, can I also? So if O12 becomes phi.
Yes.
So then you have phi d phi that should be a descendant, no?
No, this is that the IR.
I understood that O12
Yes.
in the infrared is identified with the restriction of phi.
Yes, that's true.
But then it looks like this coupling becomes descendant, no?
Becomes again?
Well, because phi
Yeah.
d phi.
Yeah, so
which is the derivative
the
of phi
usual thing
squared.
the usual thing that happens in RG flows, right, is that you start something which is relevant, and then from the point of view of the IR, it becomes irrelevant typically. In this particular flow, it becomes just marginal in a sense because it becomes phi d phi, but there is no problem, right? What was your issue with the phi d phi?
No, that if it is a descendant, should not
No,
change the theorem, and shouldn't do anything, no?
Well, but this is just strictly true when you sit at the IR fixed point. So, I mean, still there is energy. Okay. So this ends the examples. And then now I will tell you about what to do if we want to go beyond perturbation theory. And we will do that by using the numerical conformal bootstrap. So let me first say a few words about a general strategy that exists to try to look for conformal boundary conditions or BCFTs using the conformal bootstrap. So one approach that has been studied is to use this kind of crossing equation. So what is this? Maybe I should explain. So we consider a 2-point function in the bulk, and then we have two different kind of OP channels, OP decompositions of this 2-point function. One in which we push the two operators to the boundary, and then we get a sum over boundary 2-point functions, and another channel in which we fuse them in the bulk, and then we get a sum of bulk 1-point functions. Okay, so this is a strategy that always works to try to constrain boundary conformal field theories. It encounters a difficulty, which is that unlike the usual, which you might be familiar with, the usual conformal bootstrap, in this case, on this side, one lacks positivity. So the usual techniques cannot really be used. But in our setup, we are not going to do this. So this was just about other approaches, but because, of course, we can avoid doing this because of the simplicity of the theory that we're considering in the bulk. And thanks to that, we will be we will manage to just restrict our attention to boundary correlators, okay? We will basically forget about bulk and just restrict ourselves to boundary correlators. So it will be a bit similar to bootstrapping just on a local conformal field theory, which was studied by my collaborator Connor Behan in the past. He studied this problem for the long-range Ising model. Yes?
So again, in the minimal model example,
Yes.
So does the IR fixed point have Vira-Zora, or it's just global conformal?
No, it's
Right.
just global.
I see.
Yeah.
Okay.
We don't even have a stress tensor on the 2D boundary because the generators of the conformal group are given by the bulk stress tensor. Okay, so what is the idea that we are going to use instead in this case? As I was saying before to Sergio, in this case, we have two protected operators, okay, the ones that we started the discussion with, which is O hat 1 and O hat 2. I forgot to mention that on boundary quantities, it's conventional to always put hats. I don't know why. And so these two operators, O hat 1 and O hat 2, that we know their dimensions, and they are always present universally in these interacting boundary conditions of free fields. And we are going to study, we are going to use the more usual, let's say, bootstrap constraint of crossing symmetry on 4-point functions for the mixed set of correlators of these two operators. So what kind of, so this is like the crossing symmetry equation, and what kind of conformal data will enter in this crossing equation? Well, it will be the scaling dimension of exchange operators and the OP coefficients. And the input that the fact that the free theory, that the bulk theory is free, will give us, what will bias is that we can prove that this set of 3 different OP coefficients are actually related to each other. There are some exact relations. Okay, let me be a bit fast on this, but basically the idea to find these exact relations is that since now the back-to-boundary OP contains only these two operators, okay, not just one but two, but it's still simple enough that you can completely resum it, okay? So we start with 2 bulk field and 1 boundary operator. We completely resum the back-to-boundary OP, and then we impose that this mixed bulk boundary 3-point function is compatible with bulk OP, okay? By doing so, you find that actually out of these 3 OP coefficients, only 1, let's say, is an independent parameter. Well, there is an additional thing that enters, which is the ratio between the 2 back-to-boundary OP coefficients. Okay, but this is going to be the crucial thing for us. And this ratio B1/2 of the 2 back-to-boundary OP coefficients is actually constrained by unitarity to lie in an interval. Okay, so it is a bit technical, but the main message is just that the two, out of the set of 3 OP coefficients, actually we can trade it with 1 and this ratio between back-to-boundary OP. And I will now show you the results of the numerical bootstrap analysis, and I need to choose some parameterization to, let's say, parameterize the space of possibility and then cut out something. And the parameterization that is most convenient is to use this parameter that here I call delta hat, tau hat, which is the scaling dimension of the lowest spin 2 operator on the boundary. And this must be by unitarity larger than d-1. Of course, if we would be in a local conformal field theory, then this would be exactly equal to d-1 because it would be the stress tensor. But as I said at the beginning, in this case, we don't have a stress tensor, so this is allowed to be higher than d-1. So this, in a sense, measures the non-locality. And we will trade this ratio of back-to-boundary OP coefficients with a parameter. They can be traded with this parameter that we call A phi squared, which is just the coefficient in the one-point function of the operator phi squared in the bulk. And it's easy to show by unitarity that this needs to lie in this interval where till the bulk dimension. Okay, so now let me just go to the results. So this is what we found for the case of four-dimensional scalars. So let me comment a bit. So imagine that we would have been, so here we see like different number of derivatives, those of you who know about the conformal bootstrap, that eventually converge to this bound. So the purple region is the one that is allowed and everything else is disallowed. So imagine one possibility that could have happened is that, I should also say that on this end of the plot, we have Dirichlet, and on this other hand, we have Neumann. Okay. One thing that could have happened is that we could have found that the bound completely shrinked all the way to 3, which would have meant that basically there is nothing allowed. And we didn't quite get that, but you can see that in a wide range of parameter space, we are kind of close to that. So the maximal allowed dimension for the spin 2 is very close to 3, meaning that there is not much there. And however, there is a very interesting feature that appears here, which is like a kink. And as usual in the conformal bootstrap, the existence of these kinks in the bounds suggests that there might be some interacting boundary condition sitting there. At the moment, we don't have an understanding of what this boundary condition is. We don't have some perturbative construction or anything like that. That's something that's completely just born out of the conformal bootstrap analysis. And yeah, I just want to say that this resonates a bit with what we found when we tried to construct conformal boundary conditions for the four-dimensional scalar, because let's say we didn't easily construct perturbative examples. And indeed, we find that a lot of the parameter space is carved out. Questions about this? And now let me go to the result for the three-dimensional scalar. Did I mention that this was in a work last year with Connor, Eduardo, and Balt? And this is instead the case of three-dimensional scalar. We didn't publish it yet. It's a work with the same collaborators. So in 2 dimensions, there is an additional subtlety. And this additional subtlety is that the unitarity bound for scalar operators is the same as the dimension of the identity, 0. So in order to implement the numerical bootstrap, it's often convenient to impose by hand a bound, okay? Is this quantity, sorry, a gap. I mean that we have the identity at dimension 0, and then we say that the lowest dimensional scalar operator must be above a certain gap that we call delta hat 0, okay? So we gain an additional parameter that we need to somehow scan over. So what I'm showing here is what happens as we increase this gap, okay, for the scalar operator above the identity. And you see here that I depicted all these points that correspond to the minimal models coupled to Dirichlet. Remember that Dirichlet is this point. And this goes like this is 3. Sorry, this is 4, m equals 4, and this is the last one, which is the minimal model with m equals 3. But it's more interesting to actually zoom in and even reduce more the gap. So let me do that in the next slide. So what you find is that as you reduce the gap below 1, you find basically a continuous family of kinks. You see, the excluded region has this sharp feature here. Is it clear what, like the lowest one is delta 0 bigger than 1. Then as you increase it, you reduce, and you have these corners here, okay? And these corners are actually extremely close to our perturbative result for the scalar coupled to the minimal models. So what this allows us to do is that it allows us to believe our perturbative calculation all the way to m equal 4, okay? So we have a non-perturbative indication that these boundary conditions indeed exist all the way to m equal 4, even if this was just a large M calculation that we did. Unfortunately, m equals 3, no, that the Ising model apparently doesn't lead to conformal boundary condition. I guess this was the last thing, and let me just conclude with a summary. So we discussed interacting boundary conditions for free conformal field theories. We saw some example, the Maxwell theory, which led to a manifold of BCFTs, and then the scalar examples. And in the future, it would be nice to try to apply the bootstrap approach also to the vector case. It was our original goal, but we are building up to that. And okay, maybe I can stop here. Thank you.